if you were doing a regression problem, you can imagine that your values range from, say, 100 to 300. And so in that range, if this were 100 and this were 300, and your data looked like this, and your model looked like this, the bias on that model is obviously off. It should go up a little bit. Now imagine you measured root mean squared error, but you measured root mean squared error in normalized space. So if all these values were scaled to fall between 0 and 1, shifted by 100 and then scaled by 200, so they were down between 0 and 1, then you measure root mean squared error. Do you see that that has no meaning compared to this actual problem? Excuse me. What I'm trying to get at is, if you have a root mean squared error of 0.002, because you normalized the values to be really small, you did regression, you measured the error, well, that's a great number for comparison, but it doesn't tell you how far off you are on average in the actual problem. It would be kind of nice if you could measure the error in the original space, even though your neural network only makes predictions in the range of -1 to 1. How would one do that? Well, if you had one of these wrapper style models, your neural network inside the box could be making predictions between -1 and 1, but those get translated to the 100 to 300 range for the caller. And then the caller out here could measure root mean squared error and get a meaningful number that actually represents how far the model is off, how far the model deviates from the predicted labels, rather than how far the internal neural network deviates from internal numbers that the caller never even gets to see, which is kind of a meaningless metric to anybody. So I would like you to measure accuracy in this space, not in this space, because in the inner space, that's the guts of the learning algorithm, and this is the utility, useful space where your boss is going to care about, and that's the reason he's tasked you with using machine learning anyway. So therefore, that's why we do the whole untransformation step. That was a long-winded explanation. I apologize for being like that, but there you go. Answered the question. Did I get that? Yes?
So in the data we have, there's 4 different categories, right?
Yes.
When you're testing stuff like that, I think I know it's important that they're all equally represented, but I don't really understand why.
Okay. These patterns are not equally represented, and that's an important topic to talk about. So, data ECI, groups, class, waffles, wobble plot, stats, hypothyroid. Here are some stats on the hypothyroid data set. There are 3,772 patterns. There are 30 total columns. 7 of them are continuous. 23 of them have nominal values. Most of them are binary true or false things, which you can just represent as continuous if you want to. A couple of them have lots of values. You'll need to do a nom-cat transformation. There's lots of missing values. Some of them are missing all their values, so some of those columns are actually worthless. That happens in the real world. Often does. Somebody adds a database column because they think it's needed, and then turns out there's no variance in that column or something like that. But look at this. 92% of all cases in this data set are negative, meaning most people don't have hypothyroidism, which makes sense. That happens in medical data sets all the time. 5% of tested people have compensated hypothyroid. 2% have primary hypothyroid, and 0.05% have secondary hypothyroid. I don't even know what that means, but do you see how 92% of them are negative for hypothyroidism? Okay, so here's a story. My advisor tells it better, but I'll repeat as many details as I remember. someone in Arizona, I don't remember the details, so we'll just say it was the Arizona Meteorological Society, wanted to build a machine learning model to predict the weather. So they trained a model, they threw a bunch of expertise at it, they trained for a long time, they collected a crazy amount of data, they measured the accuracy. Turns out they were able to accurately predict the weather 99.8% of the time. They said, wow, we've got a really great model, this thing is awesome. They started using it, went on and on until somebody decided, let's actually go look at the model and see how it works inside. They looked inside, and basically the model always predicts sunny. Doesn't matter, it ignored all features. The bias value had gone to sunny, everything else had gone to 0, and no matter what happens, this thing predicts sunny. Why does that happen? Because it turns out the weather in Arizona is usually sunny, and if you just predict that the weather's sunny, that usually gets you a correct prediction. Well, how useful would the weatherman be if the weatherman always got up and said, I predict sunny? Well, that's a very sunny, rosy thing to say, but it's kind of stupid, right? I mean, you kind of want him to tell you, hey, there's a 1% chance of thunderstorms today. So probably don't worry about it, but at least there's twice as much chance as there was yesterday, or something. You want some kind of a prediction. Well, okay, do you remember I included the baseline learning algorithm in the starter kit that I gave you? Okay, if you use baseline, what does it do? It computes the mode, the mean of continuous values and the most common value of categorical values, and always predicts it. So if I use the baseline learning algorithm on this data set, hypothyroid with baseline, I get an average of 92.28% misclassification rate. Or no, predictive accuracy. 7% misclassification rate. Where did that number come from? Well, it's the same as that number, right? What is the point of the baseline learning algorithm? It is basically the definition of a really crappy learning algorithm. So if your neural network doesn't get 92.2% accuracy or better on this data set, what does that tell you? It tells you your bias terms are not even converging to what they should, because it should be able to predict that just by always saying negative. And that's, so 92.28 is the definition of, that's how well you can do if you don't learn. No learning is needed to achieve that level of accuracy. Let's test a better algorithm. I don't have my neural net hooked up to my tools right now, so I'm going to do a bagging ensemble of 100 decision trees that make random divisions. And we'll see how well that does. It achieved 94% accuracy. Okay, random forest is a pretty strong learning algorithm, especially with UCI data sets that are really easy. Turns out it's actually really hard to beat that with a neural net. I bet you won't get 94% accuracy. I bet you'll get closer to 92. And I'm going to be okay with that because I don't really care. But basically what I'm saying here is this data is interesting. A lot of times people figure anything in the 90s is good. That's not true, and I want to break you of that idea. In this case, anything below 92% is awful, and anything above 94% is amazing. And so there's a very narrow window of what's good results on this data set. I didn't really pick this data set because there's any achievement to do as far as the accuracy goes. I just pulled something out of the air because, one, this data set has some nasty properties, missing values and categorical mixed with continuous things. Notice some of these continuous values are in a nasty range, so they're going to need to be normalized. That's why I wanted you to work on this data set. If you can build a chart that looks sort of like this with this data, you can do it with some other data, right? So you could do this with your MNIST data set and actually get some meaningful interpretive something or others from it. You're not going to achieve great accuracy with it with a neural network because it's just a dumb problem. It's almost a linearly separable data set. But you could use the same code that generated your chart on this on MNIST or some harder data set and do something meaningful with it. So it's more of an exercise in doing machine learning stuff than it is in trying to solve this hypothyroid problem, which is actually not really a great data set for exercising neural networks. Okay. One other thing I want to talk about is stratification. So let's suppose you wanted your neural network to not predict always sunny. How would you do it? And by the way, you don't have to do stratification on this data set. And now I'm just talking about something else that you can do because you may want to. So what I'm getting at is, what do you do when you have a data set where baseline does really well, or a data set where, let's suppose you're doing fraud detection, right? Let's suppose you have cameras posted at the entrance to the University of Arkansas, and you want to detect, is this person Osama bin Laden? And if it is, a gun will automatically shoot, and if it's not, then you'll let the person pass through. Okay, that would have been funnier in 1990 something when people were all worked up about that. Well, the easiest machine learning algorithm would just learn, okay, nobody is Osama bin Laden, therefore never shoot, but that would defeat the whole point of this whole system, right? You kind of want fraud detection to just not always predict no fraud. You want it to at least sometimes say there's some probability of an intruder in the system. You want learning algorithms to be able to detect these obscure cases. So how do you do it? What if your data looks like this? There's a bunch of features, and the corresponding labels are 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, maybe another 1. The idea of stratification is as follows. We will generate some new training data where each row is randomly drawn from the original data, but we'll make sure that there's an equal number of 1s and 0s. So we'll draw one of the rows classified as a 1 at random and paste it here. And then we'll draw one of the rows classified as 0 at random and paste it here, and continue until we have constructed a full data set. And now our data set looks more like this. Right. Now suppose we train on this data, then what's going to happen? Well, the model will believe that half of the people in the world are Osama bin Laden, or that, you know, it needs to detect fraud half of the time, so this model is going to get all serious about detecting fraud, or whatever problem it is that we're training it on, because it sees a lot of it. But it's going to also learn to differentiate the fraud cases from the non-fraud cases. It's not going to just learn to predict, oh, no fraud. That would be a stupid learning algorithm. So stratification has the value of, it kind of teases the model into discerning between the two. When it's done, what the actual neural network's going to look like, though, is the output units, we're going to have probably one value here, right? All these hidden units feed into that one value. And this one value is going to be something from the range of 0 to 1, and about 50% of the time, I don't know why I'm pink now, about 50% of the time it's going to be hot and say it's a 1 because that was what it saw in your data. But in fact, we know that fraud doesn't occur that often, so we're going to say if the threshold is higher than 0.95 or something like that, then we'll say the network is actually detecting the case we're interested in, and then we'll go look at it because maybe it's not a false positive. Does that make sense? So the idea here is show it these patterns, the patterns that don't occur very often, more often, and now you can get the model to do something more interesting. With neural networks, there's a really interesting and easy way to do that. I realize I'm out of time. Just give me 30 seconds and I'll be done. You know how we have this learning rate? Well, you can adjust that learning rate, say inversely proportional to the frequency at which those classes occur. So if these ones only occur 1 out of 1,000 times, but we give it a really strong learning rate, when we do the backpropagation, it's going to strongly affect all the weights in the neural network. And when we see a very common class label, we could use a very, very tiny learning rate. Do you see what would happen? Is because these ones have more impact on it, it's kind of the equivalent of, you know how you learn faster when something really dramatic is happening? If I say, hey, pay attention, then all of a sudden, everybody's like, whoa, what's going on? And you learn more. And you're going to remember this forever. The rest of your life, you'll look back. I remember that lecture on stratification, right? Okay. You can do that with neural networks just by changing the learning rate. Wow, that came out a little more dramatic than I intended. Go have a great day. Thanks for coming. See you later.